We're going a step further from the chemical senses to talk about the body senses. The body senses provide information about surfaces touching the skin or somatosensation, about the position and movement of body parts, proprioception and kinesthesis, about pain, which is nociception, and about the position and movement of the body itself relative to the external world, which is vestibular sense. And as mentioned earlier, somatosensation, proprioception, kinesis, and nociception share significant aspects of neural processing in terms of receptor or pathways, so they will be discussed together on the somatosensory system, though arguably they are different sensory modalities. The vestibular sense is distinctively different from the other body senses in terms of its neural processing, so it will be discussed in a separate part. Again, proprioception is the sensory modality providing information about the position of body parts served by mechanic receptors in the musculoskeletal system. Kinesis is the sensory modality providing information about the movement of body parts, served by mechanoreceptors in the musculoskeletal system. We also have nociceptors, which are free nerve endings mediating perception of dangerously intense stimulation and temperature. Proprioceptors, which are mechanoreceptors in muscles, tendons, and joints, mediating perception of body position and movement. Dorsal root ganglia, which are rounded swellings that are within the vertebrae just outside the spinal cord. Each contains thousands of afferent cell bodies whose axons enter the spinal cord. And then you have spinothalamic pathway, which is the ascending sensory pathway for pain and temperature signals from free nerve endings. And then we have what's called a lemniscal pathway, which is the ascending sensory pathway for somatosensory signals from mechanoreceptors. And of course, those are some of those. Then we talk about knee-jerk reflex, which is called myotatic reflex. The reflexive extension of the lower leg following a hammer tap, for example, on the knee and a physical examination, is due to an activation of a simple reflex circuit in the spinal cord. And then we have microneurography, which is a technique for recording human sensory nerve activity using needle electrodes inserted through the skin into a nerve trunk. For example, we might have a vision of a sensory pathway in the somatosensory system. Responses from nociceptors or free nerve endings mediating pain and temperature sensations. They travel along the spinothalamic tract. Responses from mechanoreceptors mediating touch and proprioception travel along the lemniscal tract. Branching connections in Brex's laminae of the spinal cord mediate reflexive withdrawal responses to harmful stimuli. And other animals have these body senses as well. A little step up from the chemicals that underlie them. We have lateral inhibition, which is inhibition that travels across a neural network in order to impede the forward flow of activity. We have center surround receptor field, which is a receptor field containing concentrically organized regions of excitation and inhibition as a result of lateral inhibition. And then cortical column, which is a group of cells which is within a block extending perpendicular to the surface of the cortex that share a common response property, such as receptive field location or stimulus preference. We also have cortical representation of pain. We just talked about vertical organization. There's also what's called horizontal organization. Concerning somatosensory perception, We have detection, discrimination, sensation, pain. Um, a channel, for example, is a specific route through a processing system, usually carrying a specific kind of information. And so a channel is used to convey information about a particular frequency range. Their psychophysical data indicated that detection of vibration was indeed mediated by 4 channels, which correspond to the 4 afferent fiber types. So we have sensation and pain, uh, texture perception, object recognition. Uh, for example, under object recognition, we have haptic perception, which is the perception of shape, size, and identity on the basis of touch and kineticus. We have ventral, which is ventral is parts of the different brain regions. For example, results indicate that recognition involves ventral brain regions, while localization involves dorsal brain regions. So ventral brain regions are toward the front and lower part of the brain, such as the temporal lobe. The dorsal part are the brain regions towards the back and upper part of the brain, such as the parietal lobe. And then we'll get to the vestibular system. We'll be back to talk about the vestibular system. Starting to rain, so I have to get something inside. It has started to rain. Okay, so the vestibular organ is a fluid-filled organ lying in a deep cavity on the side of the skull. You have one at each side, and they provide information about the orientation and movement of the body relative to the external environment. Within that, you have what's called a vestibular receptor, which is a mechanoreceptor that produces an electrical response when hair-like protrusions are deflected as a result of external forces acting on the head. Of course, then we have the kinocilium. The kinocilium is a single tall hair-like structure projecting from each vestibular receptor. And then we have stereocilia, which are small hair-like structures projecting from each vestibular receptor to one side of its kinocilium. They are connected to the kinocilium by fine filaments. We have other organs within the vestibular labyrinth, which are the otolith organs and the semicircular canals. The otolith organs are 2 fluid-filled sacs, the utricle and the saccule, which are each in the vestibular organ. Then we have semicircular canals, which are 3 ring-shaped canals in each vestibular organ, and they are arranged at right angles to each other. Then, otolith organs, we have what's called the macula, which is the patch of vestibular receptors in each otolith organ. And then we can talk about sensory epithelia in the otolith organs and semicircular canals as well. The crista is a semicircular canal. It's a bundle of hair cells which stretches across the canal inside a gelatinous mass, the cupula, and so it's a patch. A crista is a patch of vestibular receptors in each semicircular canal. And then we have central vestibular pathways. The vestibular ocular reflex is the reflective eye movement that compensate for head and body movement in order to stabilize the visual image on the retinas of the eye. We have the vestibulocerebellar system, the vestibulothalamic system, the vestibulospinal system, the vestibular ocular system, and all these are schematic representations of neural circuits in the vestibular ocular system and other systems as well. For example, that would have to do with eyes. Vestibular perception, there's things like, for example, vertigo, height vertigo, or motion sickness. For example, an oculogyral illusion is a visual disorientation and apparent movement following rapid body spins. The Coriolis effect is the apparent deflection of the head experienced when it is moved during a body spin. And the oculogravic illusion, which is the apparent backward head tilt and visual elevation experienced during forward body acceleration. And then we have vection. Vection is the illusion of body motion caused by visual stimulation. And so just to speak a little bit more about what we just went over, we could talk about phantom limbs or modern transportation in the vestibular system, the effects of constant velocity, the effects of variation in velocity. Those are interesting things to talk about. Okay, so for example, the body senses provide information about surfaces in direct contact with the skin, about the position and movement of body parts, and about the position and movement of the body relative to outside world. The somatosensory system contains 8 different types of receptors distributed throughout the body, whose responses are conveyed to the brain along 2 parallel neural pathways. Each cortical neuron receives signals from just one of the 8 receptor types in a confined area of the body surface that defines the neuron's receptive field. Receptive fields on the hands and face are much smaller than those on the trunk and limbs. Cells with receptive fields at nearby body locations are themselves located near to each other in the cortex. Receptive field location changes systematically from cell to cell so that the body is mapped out in an orderly manner across the cortex. For example, the map is so distorted that a much larger area of cortex is devoted to some parts of the body than to others, and human ability to discriminate small differences in tactile stimulation varies in different regions of the body in a way that closely reflects the distortion of the cortical map. Concerning the vestibular system, the sense of balance is mediated by sensory responses from hair cells in the vestibular organs. Separate neural structures within each organ signal angular acceleration and linear acceleration to the head through space. The vestibular nuclei in the brainstem are major distribution centers for vestibular signals. Descending projections to the spinal cord control reflective movements of the head, neck, and limbs. Projections to the extraocular muscles controlling eye movement that compensate for head movement. The vestibular nuclei also project to the cerebellum and to the cortex via the thalamus. Mismatches between vestibular information and visual information often induce what is called motion sickness, or feelings of disorientation, dizziness, and nausea. A little bit about the effects of constant velocity and effects of variation in velocity. In a fixed say bodily movement at a fixed velocity does not generate a vestibular response. Consequently, humans can subject themselves to extreme velocities with no perceptual disturbances, as long as there is no acceleration or deceleration. Speed sensations are really due to speed change. Passengers in cars, airliners, spacecraft feel no vestibular sensation of speed even at extreme velocities. One can argue that it would make no sense to possess a vestibular system that was sensitive to constant velocity. As Albert Einstein's theory of relativity made clear, in an abstract sense, any measure of movement at a constant velocity is arbitrary since it depends on the frame of reference. If humans possessed a vestibular system that did signal constant velocity, would it report our speed relative to the surface of the Earth, or the speed of the Earth traveling in space? The latter is constant, so neural responses to it would be completely redundant. Indeed, any response to constant speed is redundant. Of course, if we went even a tenth of the speed of light, we would completely disintegrate. Humans can, of course, gain some sense of movement at constant velocity from the visual system. However, this information specifies relative velocity, speed in relation to the visible surroundings. Our perception of constant velocity movement is therefore vulnerable to variation in visual input. Underestimation of road vehicle speed in foggy conditions is due to the lack of both visual and vestibular information regarding velocity. A heightened sense of road speed is experienced in open or low-slung vehicles, such as motorcycles and race cars, where visual movement cues are particularly powerful. Concerning effects of variation in velocity, perceptual disturbances due to abnormal vestibular responses all arise from changes in vehicle velocity, either your speed or your direction. Aircraft pilots are at particular risk of perceptual disorientation, leading to inaccurate perception of the attitude or motion of the aircraft relative to the Earth's surface. I guess he meant to put altitude, not attitude. But according to one estimate, disorientation accounted for nearly 40% of fatal accidents in civil aviation in the period between 1964 and 1972. The oculogyral and oculogravic illusions described earlier in the chapter are common experiences for aircraft pilots. The oculogyral illusion can occur following aircraft maneuvers that involve complete revolutions in any of the three principal axes: turns, rolls, and spins. The pilot may experience an illusion of turning in the opposite direction just after the turn is completed. During and after such maneuvers, the vestibular ocular reflex is likely to trigger eye movements in an attempt to stabilize vision during the spin. Of course, since the aircraft's cockpit instrumentation obviously remains in a fixed position relative to the one pilot's head, such eye movements succeed only in producing visual instability that obscures the instruments. Of course, any head rotations executed during the spin heighten disorientation as well, due to the Coriolis effects discussed earlier. The oculogravic illusion can lead to the pilot mistakenly perceiving the aircraft to be at level when it is actually, in fact, banking or tilted when it. To see the aircraft as to be level when it is in fact banking or tilted when it is actually level. In the situation illustrated, the aircraft, for example, could execute a bank and turn. The pilot is subject to both gravitational and centrifugal forces, which combine to create a resultant force that is slightly tilted from gravitational vertical. The pilot may interpret this resultant force as gravitational vertical, and therefore perceive the plane to be flying straight at level. The second example is illustrated that during a catapult launch from an aircraft carrier, the aircraft is subjugated to a peak forward linear acceleration. It presses the pilot back in his or her seat with the force, a force indeed equal to 4.5 g. When combined with the downward gravitational force of 1 g, the resultant force acting on the otolith organs indicates a backward tilt of the aircraft, though perceived tilt is much less than would be predicted by the direction of the resultant force. Inexperienced pilots, for example, may attempt to compensate for this apparent tilt by pitching the plane down toward the seat. The extreme disorientation experienced by pilots can impair and confuse their motor control to such an extent that they report an invisible giant hand interfering with their command of the control column. Flying instruction draws attention to the dangers of misinterpreting vestibular signals. Pilots then are taught to avoid flying by the seat of their pants and to rely on instrumentation for information about the attitude and motion of the aircraft. And of course, that's quite interesting. You have the centrifugal force. For example, let's say you're going from a position of equal at an equal level to the ground. You go to a left tilt. The gravitational force is still bringing you down, but the resultant force is leading to a centrifugal force. And so as gravitational force brings you down, you have the force of linear acceleration at the end, and then you have the resultant force that tilts you up. So there you go. That was on the body senses, ending with the effects of constant velocity and effects of variation in velocity.